Hello everyone and welcome back to the Nebula Space Organization's the Aurora Academic Journal. I am Snehadir Kumar, CEO of the Nebula Space Organization.
And I'm Rajshri, Marketing Lead of the Nebula Space Organization.
Today we have a special guest with us, Dr. David Wineland, recipient of the 2012 Nobel laureate in Physics for his groundbreaking work in trapped ions has revolutionized the quantum physics and paved the way for countless advancements in areas like quantum computing and atomic clocks. Hello, sir. How are you doing?
What? Sorry, I just having a little trouble hearing or understanding, so speak a little slower, maybe.
Sir, how are you doing, sir?
Oh, I'm doing fine, thanks.
Amazing, sir. So shall we start with our questions?
Sure.
Sir, could you tell us about your research topics?
I'm sorry?
Could you tell us about your research topics?
I just didn't understand, I'm sorry.
Sir, could you tell us about your research topics?
Recent topics?
Yeah.
Well, I mean, for, quite a while, I've been working on two different things, and one is atomic clocks, and more recently, trying to implement the basic ideas of quantum computing. So I'm mostly focused on these, trying to, play with the ideas of quantum computing.
So, what motivated you to study physics, and what was your journey from being a student to reaching the pinnacle of physics, like receiving the Nobel Prize? What was your journey?
Well, I mean, I can actually, if you want, I had a few view graphs on my path. Shall I try those? Just 1 second. I'm going to try to bring those up. Oops, let's see. Sorry for the delay here. Let's see.
Absolutely fine, sir. Please take your time.
Okay. So I can maybe bring this up. Let's see. Okay. Can you see that?
Sir, is
Oh, I
this
got it. I need to share my screen. Sorry. Okay, let's see. Let me just see. I'm sorry about this. I'm forgetting how to share my screen here.
sir, there's a green option in the below the screen of the Zoom meeting. Share screen.
Yeah, that's what I'm looking for, but sorry. I'm not seeing the, let's see. I'm very sorry about this. I'm just not seeing the icon for the share screen.
Sir, below the
Wait.
Zoom, there is a
Yeah.
green option. Share screen where you can share. I think it can appear now.
Yeah, but somehow I'm not seeing that.
Oh,
It's okay. You can do it the way you want to, like verbally or anything.
Oh, here we go. I finally got it, I think. Let's see. Well, I'm clicking on share screen and nothing is happening. So Ah, I'm really sorry about this.
It's okay, sir.
Absolutely fine, sir. You can do it your way.
Ah, I'm really sorry about this.
It's okay, sir.
Unfortunately, I have a new laptop and I'm not quite familiar with it. So, I'm really sorry about this. I should have practiced this.
Okay, sir. It's absolutely fine. So would you like to continue verbally?
I'm sorry.
So would you like to continue verbally, like without that thing?
Yeah. Okay. I'm really sorry about this. I
It's
just,
absolutely fine, sir.
let's see. I don't know why I'm just not seeing can't find the share screen here. Ah, no, that isn't working either. This is really annoying. I'm really sorry about this.
Sir, would you like to tell us about your journey verbally? Like, what was the journey from being a student to reaching the pinnacle of physics?
And now I'm still having trouble understanding what you're saying. So,
Okay, sir, I was saying that would you like to share your journey verbally from being a student to reaching the pinnacle of physics?
I, I'm sorry. I'm just having trouble understanding what you're saying.
Sir, actually, we're saying that what motivated you to study physics and what was your journey from being a student to reaching the pinnacle of physics?
Well, okay. Well, it's a long story. I can say a little bit of that. My parents were, they lived through the Great Depression in the United States. That was from basically 1930 to 1940. And so they were lucky because they had jobs. A lot of people lost their jobs. But anyway, with this background, they always emphasized that my sister and I would go to college. And the main reason was so we could have a good job later. And so anyway, they put an emphasis on education and, of course, to, maintain good grades in school. And I always liked school, so it wasn't, too big of a problem to focus on school. But anyway, and my father also, he was a engineer, and when I was very young, he played, little math games with me, and that was sort of stimulated my interest in mathematics. But on the other hand, even though all through high school, all through grammar school and high school, my parents were, gave me a lot of freedom to explore. And so, for example, when I was a young kid, I played with model airplanes, and then when I got into high school, actually, I got my first car when I was 14, and I couldn't drive it. I found this car so I bought it, but my father had to drive it home, and then I spent the next 2 years working on fixing it up and needed a lot of repairs. And so anyway, that got me into making things with my hands, and actually that went all the way through high school. My friends and I were interested in cars and motorcycles, so I always had that behind me. But anyway, when I started, or I should say, when I was in high school, I took the first physics class, and when I was a senior, and what I found about that is that I just liked the way relatively simple mathematics could explain, the things we see around us. And so that got me interested in physics. but when I started college, I was at the University of California. I was first at there are several campuses of University of California. And for the first 2 years, I went to the Davis campus, and that was had been an agricultural school primarily. So, but it was close to where I lived, and so for my first 2 years. But about halfway through after my sophomore year, it was clear that University of California, Berkeley was sort of the place to be for physics. So basically, I went my last 2 years to Berkeley, and it was really easy. I was in the University of California system, so I just had to file a form, and then I was accepted at Berkeley. So I spent my last 2 years there, and then when I was at Berkeley, a couple of my teachers that I liked, they were talking about places to go for me, and one of the faculty, he had been to Harvard, and he's anyway, so he stimulated my interest, and so I applied to Harvard, and I got in. So that's where I did my my graduate school, and so anyway, I actually started as a math major in college. And then but when towards the end of my undergraduate school, I had switched to physics. I just liked physics better. So anyway, I went to Harvard as a graduate student, and I worked for a person who is one of the most famous atomic physicists of the 20th century, is Norman Ramsey, and at that time, around that time, just before I came there, so I started there in 1963. And, but anyway, when I arrived there, just shortly before that, he and his colleague, Dan Kleppner, who later went to MIT, they had invented and demonstrated the first hydrogen masers, and masers are just like lasers. The M stands for microwave, but rather than light as in a laser. But the principle is exactly the same. It's just the frequency is different. In fact, a little bit of history is that the first devices that operated like lasers were actually measured at microwave frequencies, so the principles are very much the same. But anyway, so that's where I got my degree there, working on hydrogen maser, and so that was it. I was there for about 5 years, and then or 4 years, sorry, as an undergraduate, 4 years, as a graduate student, 4 years. And anyway, it was sort of natural. I think most of my classmates that, after graduate school, we would go to, take a postdoctoral position. And I took a position in University of Washington. It was with Hans Damelt was my advisor, and he and Norman Ramsey actually shared the Nobel Prize in 1980. Now I'm forgetting. Anyway, 1986. But Norman Ramsey received the prize for the invention of the maser and other atomic physics techniques. And my advisor at the University of Washington, Hans Damelt, he had done a lot of the early development with ion traps, atomic ion traps, and so. That's what I actually, when I was with him, I worked on trapping electrons, but the principles are very similar. And so it led to being able to when I went to, after my postdoc position, there was I had hoped at the end of my postdoc position, I hoped that I always wanted to go to a university and become a faculty member. And anyway, I actually got I had a couple of interviews and offers, but they were good places, but they weren't that, they wouldn't be able to give me really strong support. And so anyway, but at that time, an opening came up at the NIST, the National Institute of Standards and Technology. And that's there's two branches. One is in Gaithersburg, Maryland. The other is in Boulder, Colorado. So this one was in Boulder, Colorado. And basically, when I went there, I was, they, for example, one of my first tasks was they had built a new atomic beam cesium standard. And so one of my first tasks was to work with one of the other guys there to make it work properly and, figure out all the errors and set an accuracy limit on it. And so that was where my first year and a half or so was doing that. But when I was a postdoc with Hans Stamos, I had this idea about laser cooling. And so, I talked about with him about it a little bit there. And we wrote this paper, which was kind of an obscure paper. So I don't think too many people read it. But anyway, what was nice when I went to be a when I went to the National Institute of Standards and Technology, my first job was to make the cesium clock work. But then my boss at that time was, he knew about the idea of laser cooling. So I was lucky there because he was able to get some money so we could actually build up an apparatus to demonstrate it. And so I would have to, so it actually didn't take us very long. I teamed up with another fellow there. His name was Bob Drillinger. Anyway, he knew a lot about lasers and I knew about ion trapping. So we teamed up together, and actually after we got the money to build this apparatus, it only took us about 5 months to put this apparatus together and demonstrate laser cooling. And so I'd have to say that was without a doubt, that was, one of the highlights of my career, because it was the first time, I had a project where I was guiding it rather than my advisors. And so anyway, so that was certainly a highlight of my career. And so anyway, this idea of laser cooling is now used in a number of contexts. It was certainly important for atomic clocks because, just to give a rough idea that, what it affects atomic clocks in different atomic clocks in different ways. But for this, we've made started making clock based on atomic ions. And there the idea is, the students listening here would be able to, in a short time, I could easily teach them how it worked. But the basic thing is there's some electrode structure that we apply static and oscillating electric fields or potentials to, which creates electric fields that provide a confining region. And so basically we would put our ions in there. Our first experiments were on magnesium ions because they had the lines that we needed for the laser cooling were more accessible than other ions. So, but anyway, so we were able to show these basic ideas. And so, but the basic ideas about laser cooling, now, certainly they permeate a lot of atomic physics, and they're certainly important for atomic clocks. And the main reason initially, and still true today, the reason why it's important for atomic clocks is that, let me just, in the context of trapped atomic ions, you can think of the ions as, a two-dimensional picture of an ion trap is like marbles in a bowl. And so we have a three-dimensional version of kind of a bowl like that. And so basically when we put ions in there, they can rattle around if they have finite energy and they collide and so on. But so the idea of laser cooling is that we could reduce their temperature. And the main reason that was, first of all, it was interesting and led to a lot of other things. But the reason it was important for atomic clocks was that it suppressed the temperature and therefore the motion of the ions. And the reason that's important in all atomic clocks is that if the atoms or ions are moving, there's we have to worry about Einstein's second order, time dilation shift. And so that was really, certainly it's employed in all atomic clocks now, at least accurate clocks is to use laser cooling. And so it was certainly important for that. And so anyway, we, throughout my career at NIST, I was, which was about, so my time at NIST was about 43 years. And so I was there until just a few years ago when I came to the University of Oregon. But what I wanted to say was that at NIST, we further developed these ideas of cooling. And one of the things that was interesting is we could actually, as I say, if we have a single ion on the trap, it's basically it's a charged particle in a harmonic well. And so, as we cool the ions down, lower and lower temperatures, we have to worry about the quantized motion of the ions in this well. So eventually we were able to, extend the simpler ideas of laser cooling. And so we could finally cool ions down to their motion ground state. So that, and we could, when we did that, we basically didn't have to worry about the Doppler shift due to the time dilation shift due to atomic motion. And I think that, the ideas of laser cooling now, used in a lot of neutral atom experiments as well, not just for atomic clocks, for studying collections of cold atoms and so on. So anyway, it's been a key part of my research for a long time. And in about 6 years ago now, I came to the University of Oregon, and the reason was I was completely happy at NIST, but my wife has some, health problems, and she was bothered by the altitude in Boulder, Colorado, being in the mountains. And so we came here, and it's really a nice place here as well. So I'm working, now I'm working, I was able to bring in a younger, person who was actually a postdoc at NIST when I was there with me. And anyway, so he's, I'm actually working with him now, and we, we have students who are working together, and so been setting up a lab here. So anyway, so that's now my life story almost.
That's really a wonderful journey, sir. That's really inspiring. Sir, moving on to the next question. What were the emotions upon hearing that you're gonna be a Nobel laureate?
Say again.
What were the emotions upon hearing that you're gonna be a Nobel laureate?
I'm just sorry. I can't, I just maybe speak a little slower. I just don't understand.
Sir, what were your emotions upon hearing that you will be a Nobel laureate?
I've heard the part on Nobel laureate. What was the first part of the question?
Sir, what were your emotions upon hearing that you'll be a Nobel laureate?
Okay, yeah. Well, it certainly was a surprise, and in fact, I think, it's always interesting. We all, as physicists, we always interested to see what the new Nobel prizes were, and some of my colleagues even stay up at night, when it's announced. So it's announced in the late morning in Stockholm, Sweden. But that's anyway, and so what the procedure is, they but they'll have the Nobel committee will have decided who the recipients are, but they only release it to the news just shortly after they call the recipients. So you probably know I shared the prize with Serge Haroche, who is an atomic physicist from Paris, and I had known him for quite a while. So it was really nice that we shared it together. But anyway, so when this call came in, it was late morning in Stockholm, but it was 3:30 in the morning, and I would have slept through the call, but my wife heard it and woke me up. So then, the fellow that I talked to, it was only very short because he knew that reporters would want to be calling, and so even during this call when we were talking, you could hear clicks on the phone, where the reporters were trying to call in, and so this was still early morning for me, and then so after I took a few calls from reporters, but then I went to work, and they were going to arrange a press conference which would take care of most of the reporters, and so that's what happened later. Pardon me, later in the morning, there was a press conference, and I could, most of the reporters could get what they wanted from that. So actually, oh boy, sorry, I'm losing my voice here, but so one of the interesting things was that this press conference is in the morning that day, and there were all during the day, I was there. My calls were coming in my phone, and I only answered a couple, but the rest of the time I eventually answered all the calls that came in. But what was kind of funny at the end of the workday, I was about ready to go home, and I heard another call come in, and I thought, well, I'll take this one call, and that the fellow says, "Is this David Wineland?" And I said, "Yeah," and I said, "Yes," and he says, "This is Air Force One." So it was President Obama on his plane giving me a call. So that was a really neat experience for me.
This it really is.
So it was absolutely amazing, sir. So coming to the next question, what are your views on Google and IBM's quantum computing?
Just say it again slowly.
So I asked, what are your views on Google and IBM's rise in quantum computing?
I heard quantum computing, but I'm sorry, I just didn't hear the.
So what are your views in the rise of Google and IBM's quantum computing?
I still didn't understand the first part of the question.
Sir, what are your views on Google and IBM's rise in quantum computing?
I heard something about Google, but I still don't.
Sir, your views on Google and IBM's rise in quantum computing. Google and IBM's.
I'm sorry, I'm just not hearing very well.
Sir, is it audible now?
So are we audible?
Sorry?
Sir, what are your views on Google and IBM's rise in quantum computing?
I'm really sorry. I'm not understanding the first part about your question.
So we are asking for your views, what you think about the rise of Google's and IBM's quantum computing.
Oh, wait, are you asking what I think about the ideas of quantum computing? Yeah. Well, I mean, I think that, I think everybody's, I think for everybody, some of the ideas have been posted about quantum computing. I think everybody believes the basic ideas, and we can demonstrate a lot of the features but at this stage we just we can't do things well enough or do use as many qubits to do something really interesting. But I think it's certainly in the future that we'll actually be able to do interesting things. And so a lot of certainly one of the historically one of the things why the government got interested, as you probably know, is that Peter Shores, who's a mathematician who's now at MIT, he came up with an algorithm for factorizing large numbers, efficient factorizing of large numbers. And the reason that's important is one of the most popular encryption schemes, coding schemes, gets its security from the inability to factorize large numbers. So, you can imagine that certainly the idea of the algorithm that he came up with, everybody believes it's sound, but, we're still in the point where we just can't manipulate enough quantum bits, to actually realize it. But that was certainly the start of it. And it's certainly because of the consequences for, encryption systems, that's why the government got very interested, which was nice for us because we get a lot of funding to develop some of the basic ideas. And we're still in this, I would say, with this initial, this initial application. I think, that's still true, but I think even talking to Peter Shore, the inventor of this algorithm, within the last year, he says that that now mathematicians are coming up with new schemes, which, as far as he knows, a quantum computer can't crack these codes. But I think nevertheless, I think most of what most physicists think, is that where the real application anyway is going to be in simulating other systems that, with a quantum computer. And this goes back even to, Richard Feynman, who apparently came up with the story with him was that apparently he was at some conference about reversible computer algorithms, and which was certainly related to quantum computing ideas. And anyway, he was asked, well, what's the best way to build a computer? And he just threw out the idea, well, it should be a quantum system if you're going to solve quantum problems. And so basically, anyway, that's a little side note, but basically he what he was saying is that I think the real and what I think most of us feel now is that the real application is to do complex quantum calculations that will help the world. And certainly one of the things people think about in chemists, they're interested in the ideas of quantum computing. They think they'd like to. One of the grand things that they might be able to do is, for example, figure out the action of some chemical that might be used in, say, drug therapy or something like that. And they could, if they could simulate the quantum behavior of the system, then, that would obviously have a lot of, important consequences for society. But I think just as physicists, there's many problems that quantum physics problems that we don't have with classical computers, we don't have the power to solve these problems, but, and we don't yet with the quantum computers, but I think that's the hope for quantum computers.
Great, sir. Sir, if you don't mind, can we resend the link to you again? Because the meeting time is going to end and we can have optimal time. If I can send you the meeting link again in the email.
I'm sorry? Just say again.
Can we send the meeting link again in the email? Because the remaining time is 3 minutes. So we can have a lot of time to talk again.
Okay, so I mean, but do you want to, I'm sorry, what do you want to, but you have to sign off now, is that right?
No, sir. The remaining time in this Zoom is for the total time is 40 minutes. So the remaining time is 3 minutes. So if we can resend the link to you so that we can talk again, because there are 3 minutes remaining. So we can resend the
Okay,
link to in the email, and then we can rejoin in this meeting.
okay, so are you gonna, should I sign off now and you'll send me another link?
Yes,
Is that
sir. Yes,
right?
sir. Yes, sir. I will
Okay,
resend the link, and then we're rejoining in the meeting.
okay, so you'll send me a link and I'll log on again, is that
Yes,
right? Okay,
yes,
so I'll sign off now and
yes,
I'll
sir.
look for
And
the link.
yes, and then
Okay,
Zoom link. So,
thanks. Yep. Okay.
okay, sir. Moving to the next question, Rashi can continue.
So, what do you see your research intersecting with other scientific fields like medicine and material science?
I heard the last part about, just say it again.
So, how do you see your research intersecting with other scientific fields like medicine and material science?
Well, if I understood your question, this was basically what I was trying to say just before we had to end there, is that I think, this, the thing that's going to be have most impact in the long term is not coding, cracking codes, but, to simulate other systems that have value for other reasons. And I gave example of, say maybe some chemicals that could be used in drug therapy, and that would be a great thing. So I think that's where most of us, feel the application is. And in fact, what's interesting is that, I think, I forget whether I said this, but anyway, maybe I'm repeating myself, but, I think now even Peter Shor says that, the cryptographers are coming up with schemes that he doesn't think a quantum computer could help. Yeah, I did say that. Anyway, so I think that's where that's where the real impact will have, and it will be in the long term. And I think I think the ideas that people have, I think everybody feels everything is the mathematical ideas are sound, but it's just that it's getting systems that are good enough to carry out these complicated, lengthy operations. That's where the problem is. And I think, sometimes people ask, well, when are we going to get a really useful quantum computer? And I don't think anybody knows that answer. But I think most of us I would feel very surprised if the problems we have now aren't eventually solved, and that we really will have useful quantum computers. But we'll see. I guess when I say that, what I mean is that there doesn't seem many fundamental barriers in the problems we have in our systems. We know generically what the problems are. They're straightforward to describe, but how we suppress the problems is, that's the hard problem. So,
Sir, what are your some of the biggest misconceptions about quantum computing that you would like to address?
I'm sorry, say again.
Sir, what are some of the biggest misconceptions about quantum computing?
What are some of the biggest
Miscon
discussions?
yeah.
Yeah, well, I mean, I don't, I I don't know whether I could say there's, identifiably these big discussions, but I think there's, that just to try to say again, I mean, whether it's atoms or superconducting Josephson junctions or something like that, they all they're susceptible to noise, and it's just, I think we have ideas how to suppress it, but so in some sense it's just this is probably too simple to say, but there's a lot of careful engineering that has to be done, because I think, as I said before, I think I think we all feel comfortable with the ideas of quantum computing, but and it's just making the devices that can implement these algorithms is the problem. And it's just boils down to making better and better, Josephson and junction circuits, or better and better ways to manipulate atoms or ions, that sort of thing.
Right, sir. So, moving a little bit off from these physics and stuffs and asking you a question, we'd like to know what are your personal passions and hobbies outside of physics?
Oh, well, maybe I mentioned that when I was a kid, I played with model airplanes and then with cars. So actually, when I was in graduate school and when I was a postdoc, that was about 9 years total. I mean, my big hobby then was racing motorcycles. So I think about half of my Sundays for during that 9 years, I was racing motorcycles somewhere on the Sunday. So anyway, but I what I tell students, I mean, that was what did it for me. But I think the important thing about is that the students are they're going to be studying hard on both the undergraduates and graduates, and later when they become professionals, and it's hard work to make progress. And I think I guess my only example I think what I say motorcycles for me is it was just a great release to get away from thinking about problems for a while, and it doesn't have to be that, but some people like to take a walk or go skiing or something like that. But I think it's important to I think a tendency for all of us is just to get especially when we're having trouble solving a problem, we tend to work even harder and harder. And sometimes it's a good idea to just get away from it for a little while. And so that was my way of doing it. But there's other ways to do that, of course. And I think, but the students should find some way to turn their minds off a little bit, as they progress. So.
Here it is, sir. Sir, do you have any words of inspiration for our listeners, especially the ones interested in science and physics?
I mean, I think that, I mean, I think, you're always going to run into times when you struggle with something, whether it's, early when when you're school, it might be a class you're struggling with, or later, if you're an experimentalist, you might struggle with trying to make some apparatus work. But I think, the main thing is I think that's gonna happen. And you just, that you have to, I think you have to take a break, which is a reason for, just turning your mind off to things like that. But I think you have to expect that. But I think, perseverance usually always wins out. So, there'll be times, when, you get discouraged. And the other thing I would say is sometimes, especially for, in experimental physics, you may have some idea about something you're trying to put together, and, you'll find that, the basic idea was sound, but you may find that as more and more you work on it, it just becomes, technically impossible or extremely difficult. So you have to be willing to change directions. And I think that's fine. And, you shouldn't consider it a failure. It's just that you find you need to go different directions. And often what happens is if you find it, running up against a dead end on some problem, you'll maybe take a turn, and it may lead to even something more interesting. So don't be discouraged. Like you do want to be able to change direction if necessary, but other than that, I think you're always going to be able to find something interesting, some interesting extension of what you're doing.
Of course, sir. So, sir, coming to the last question of this session, Did you have any mentor or role model who influenced your career path?
Role models? Yeah, well, certainly I think, my thesis advisor, Norman Ramsey, I mean, he was really, first of all, he a very smart guy, but also he is extremely nice person, so he was nice to everybody. He really was an amazing person, and that I think it's nice to have that the people you work with may not always be as encouraging and so on like that. But I think for the most part, I think people will help you get through the things you're dealing with. And so, I mean, that it does, as I say, you'll reach some difficult stopping points, but I think that's part of the process. It's nothing to get discouraged about. So, yeah.
Thank you, sir.
So it was an honor meeting you. Thank you for accepting our invitation.
Well, my pleasure to do it. And for the students out there, I wish them all good luck in their careers. So, yeah.
Sure, sir. Thank you very much,
Thank
sir.
you so much, sir.
My pleasure. Thank you. All right. Bye-bye.
Good day.